Welcome to this presentation in the series, Electronics, the Story of One Human Lifetime, presented by David Beams and Gary James. I am David Beams, retired Associate Professor of Electrical Engineering. This presentation describes basic operating principles of the bipolar junction transistor and the Field-Effect Transistor, two devices which changed the world. Let's let Nikola Tesla pose the questions that we will address in this presentation. How do we make a semiconductor amplifier? What are the electrical properties of a device like that? And how would we apply these devices to digital logic? The beginning of the solid-state revolution was with these inventors of the transistor. Their invention was later renamed the bipolar junction transistor, or BJT, to distinguish it from the field-effect transistor, or FET or FET, which came later. A brief description of the operation of the bipolar transistor. We'll let Nikola take care of the details. A BJT has three terminals and two junctions. The designations NPN and PNP tell the arrangement of the device: emitter type, base type, and collector type. The base emitter junction is forward biased. Note the polarity of the base emitter voltage VBE. And the base collector junction is reverse biased. Notice the polarity of collector base voltage VCB. The emitter injects electrons into the base, and these electrons move across the base by diffusion. Any electrons that diffuse across the base are swept into the collector by the electric field present at the collector base junction. These electrons are removed from the collector by the external batteries, or battery, and this constitutes the collector current. Most of the electrons that are injected by the emitter into the base will diffuse across the base, but a small fraction, usually less than 1% of the electrons that are emitted into the base, will recombine in the base. These electrons will be removed by the external battery and produce the base current. This small recombination in the base permits the base current to control the collector current. Let's look into this phenomenon. Now let's change the base emitter voltage slightly so as to double the base current. For a BJT operating at 300 kelvins, that requires increasing VBE by about 18 millivolts. But the ratio of electrons crossing the base to those recombined in the base is fixed by the structure of the base. So doubling the base current will result in doubling the collector current. So say that 1% of the electrons injected are recombined in the base, and let's start with a base current of 10 microamps. That would mean that the collector current is 99 times larger, or 990 microamps. Well, now let's change VBE to give a base current of 20 microamps. The collector current is still 99 times larger, but now that means 1.98 milliamperes. So a change of 10 microamperes in the base current results in a change of 990 microamperes in the collector current. The BJT acts like a current-controlled current source, and it's capable of amplification. But since changing the base current requires a change in the base emitter voltage, we can also speak of the BJT as possessing transconductance. A change in the base emitter voltage produces a change in the collector current. Now we'll look at the measured electrical characteristics of a common NPN transistor. This graph shows collector current in milliamperes on the y-axis versus collector to emitter voltage on the x-axis. There is one curve for each of four different values of base current, from 10 microamperes up to 70 microamperes. And we see a direct proportionality between the collector current and the base current. You know, the spacing of these curves is for a 20 microampere change in current at each step. You see we get an approximately linear change in the collector current. Well, for example, at 5 volts collector to emitter voltage, right here, changing the base current from 10 microamps, this yellow line, to 30 microamperes, this orange line, changes the collector current from 2.6 to 8.5 milliamperes. which gives us a current gain of 295. Changing the base current from 30 microamperes to 50 microamperes changes the collector current from 8.5 to 14.5 milliamperes, which would be a current gain of 300. Notice that the collector current is almost independent of the voltage of the collector. As long as the collector-based junction is reverse biased, it makes little difference in the collector current, as the simple model, which collector current is driven by injection at the emitter, would predict. But when the collector-emitter voltage becomes low enough, the collector-based junction becomes forward biased and the collector current starts to fall off. This is known as saturation. The BJT is used as an amplifier in this normal mode of operation. In digital logic, however, we switch it between cutoff, that is no conduction at all, and saturation. Digital logic using BJTs took astronauts to the moon in 1969. But digital logic with BJTs had significant limitations. Beginning in the late 1960s, a newer type of transistor, the metal oxide semiconductor field-effect transistor, or MOSFET, usually shortened to just FET, began to displace the BJT. This is a cross-section of a FET. The FET is built on a doped semiconductor wafer. Here we have P-type silicon. It's possible to start with an N-type substrate. We will see that later. It includes an N-type region of material, which we call the source, another region of N-type material called the drain, a thin insulating film, usually silicon dioxide, although more exotic insulators are sometimes used, and an electrode on top of the insulator made either of aluminum or doped polycrystalline silicon. The region under the insulator between the source and drain is called the channel. A P-type substrate is always operated at the lowest voltage in the circuit, so neither of the two junctions, source to substrate or drain to substrate, is ever forward biased. We've shown the source and substrate here as both being grounded, and we will start with the gate to source voltage, VGS, at 0. So we have two reverse biased junctions, means that there's no current in this drain or the source. Nicola has an important word to add, that the FET is actually a 4-terminal device. So now let's make the gate to source voltage negative. That has the effect of increasing the concentration of holes in the channel, making it even more P-type. We are accumulating holes in the channel, but there's still no conduction. Now let's put a small positive voltage on the gate, but less than what is known, and we'll understand in a moment what that means. Let's put a voltage on the gate which is less than the threshold voltage. This decreases the concentration of holes in the channel, so the channel is said to be in depletion. We are also increasing the concentration of electrons in the channel, but holes still dominate, so the channel is still P-type and there is still no conduction. Now, we will increase the positive voltage on the gate so the gate voltage exceeds the threshold. The electron concentration in the channel increases, and the hole concentration decreases to the point that the channel is now N-type. We say the channel has entered inversion. Thus, a band of N-type material extends from the drain to the source, and the FET can now conduct current between the drain and source. The threshold voltage is the gate voltage at which the channel enters inversion. Now, one note, this shows the case in which the drain voltage is relatively low. This is an N-type transistor which conducts current by means of electrons in its inverted channel. It is called an NMOS or N-channel MOS device. Note that the NMOS device is built on a P-type substrate. Here we have the case, however, where the drain voltage, we've increased the drain voltage, And as we move towards the drain, the electron concentration in the channel tapers off as we move closer to the drain. And when the drain voltage becomes large enough, I'm not going to specify exactly what that is here for the moment, but actually you'll have to wait till you take electronics to see specifically what that means. But when the drain becomes large enough, the channel excess electron concentration can taper to zero, and the channel can enter what we call pinch off. But pinch off does not stop the drain current. Instead, it becomes almost constant, independent of the drain voltage. Now here we have the measured electrical characteristics of an N-channel FET or NMOS device, showing drain current in milliamperes versus drain voltage. Both the source and the substrate were at 0 volts when these characteristic curves were measured. There are 6 curves, 1 for each gate voltage, from 1 volt to 6 volts in steps of 1 volt. So notice the separate curves for each gate voltage. And notice how the current is dependent upon that gate voltage. And this region, where we have the drain current largely independent of the drain source voltage, is a result of the pinch-off phenomenon. The FET is said to be in saturation when it operates with its channel in pinch-off. Just as a note, saturation in a MOSFET does not mean the same thing as saturation in a BJT. But when the drain voltage is low, the channel is not pinched off. The FET is said to be in triode when it operates with a continuous channel. The chief use of the FET today is in digital logic, where it is switched between cutoff, no conduction, and triode operation. If we want to use the FET as an amplifier, we'll operate it in its saturation regime. Now we'll look at a specific MOSFET structure commonly used in digital logic. Previously, we had looked at a MOSFET fabricated on a P-type substrate with an N-type source and drain. Well, we can also make a MOSFET with an N-type substrate with P-type source and drain regions. Since the channel is inverted to P-type, when this transistor is conducting, it is known as a P-channel MOSFET or a PMOS device. We can build both N and P-channel devices on the same substrate by building one transistor in a well. Here the P-channel device is built in an N well, which is embedded in the P-type substrate. Combining P and N-channel devices on the same chip makes a CMOS structure, in which the C stands for complementary. CMOS is the most widespread form of digital logic today. And Nicola can sum it up for us. You have a basic understanding of semiconductor physics. To give you some idea how rapidly the solid-state technology has advanced, only a half century between the first transistor and the Intel Pentium Pro. According to the Institution of Electrical and Electronic Engineers, commonly known as the IEEE, it is estimated that the MOSFET is humanity's most replicated invention, even exceeding the number of characters printed in books since the invention of movable type. Well, thank you for watching, and join us for the next presentation where we will show some examples of historic solid-state device technology.